So folks, in the previous video we said that we're giving an overview of inverse functions. But before we could talk about inverse functions, which is this process of taking a function and reversing its direction, essentially, that we had to determine whether or not a function actually has an inverse. Not all functions are invertible. And so we introduced this topic called one-to-one, and I worked through a couple of problems where I was asking you to determine whether or not these functions were one-to-one, and then hopefully you took a look at these problems here. Let's go ahead and do them together. If I were to look at the graph of this function right here, the graph of negative x squared plus 2, well, the graph of this function looks something like this. So this is not one-to-one, and one way you could say that is that it fails the horizontal line test. That's one justification for that. Okay. If we were to look at h of x, well, h of x is the function the log base 2 of x. So we will review logarithms specifically, but hopefully you remember the graph, and if not, this is something worthy putting on a note card. The log functions, regardless of base, always pass through the ordered pair 1, 0, and if their base is greater than 1, they're going to have all logarithm functions before transformations have horizontal line, vertical asymptotes right here, and their generic shape, if their base is bigger than 1, would look something like this. And so here we can see again that this is a one-to-one function. This is one-to-one. And another way you could say that is that it passes the horizontal line test. So what I mean by passing or not passing the horizontal line test, I'm talking about for every horizontal line that I could draw, notice that that horizontal line never intersects the graph more than once. If it doesn't intersect the graph at all, that's okay, but it never intersects the graph more than once. Whereas over here, we could see that we fail the horizontal line test. I'm going to delete that because it looks pretty messy when you keep all that in there, but hopefully that gives you an explanation of that test. Okay. These next two examples are really important, I think, because it's where it lets you know that this topic can sometimes get a little bit more difficult. So for letter D here, we've got k of x is equal to minus x squared plus 2. This is the same function that we had up above here, but in this case I have this restricted domain. And if we were to look at the graph of this function here, the graph of this function looks something like so, because we're only graphing it for x values that are positive. Remember, these are the places where x values are positive or equal to 0. I should be careful there, or equal to 0. That's where our x values are positive or equal to 0. So that's the only portion of the graph that I graph. So even though this is a quadratic function, it is one-to-one, this restricted one. Okay. Now, I could show you the graph of this function, and maybe we will here in just a second, but there's an easy way to see that this function is not one-to-one. Let's just check that. If I were to take L of 1, that would be the log base 2 of 1 squared, which is the same thing as the log base 2 of 1, which is equal to 0. Log for any base of 1 is 0. If I were to take L of negative 1, that would be the log base 2 of negative 1 squared, which is equal to the log base 2 of 1, which is also equal to 0. And so what did we see here, folks? We saw that two distinct inputs ended up giving me the same output. And so we are not one-to-one. If you wanted to look at what the graph of this function looks like, the graph of this function looks something like this. And you can see that this graph fails the horizontal line test. So this just is a little bit of a warning here. Here this function is, where the domain is all real numbers, it is not one-to-one, but on a restricted domain it is. And here we have a one-to-one function, but when I composed it with the x squared function, meaning in place of x I replaced it with x squared, I got something that wasn't one-to-one. Okay, so here is the definition of the inverse function, and it's actually precisely what we said on this first page. The inverse function is the function that takes this, so here in the original function, a got mapped to the number 1. The inverse function is the function that takes 1 to a. That'll be the definition of the inverse function. All right, so again, the definition of an inverse function, first of all, requires that our function be one-to-one. And then in order to create this new function, which we'll call f inverse, which will be the inverse of f, the way we work is that for every ordered pair that looked like this, remember this was an ordered pair that looked like AB, we define a function that does the following mapping. It takes the input B and maps it to A. So this is the domain range flip-flop that defines a function inverse. Why do we need a function to be one-to-one in order to find the inverse? That's an interesting question. So let's look at this example right here. So if this were my function where we have, maybe we've got 1 and 2 and 3, maybe over here we have A and B. So maybe 1 gets mapped to A, and then let's say 2 goes to B and 3 goes to B under this function here. If I want to try to construct f inverse, so let's try to make f inverse. If I want to try to make it, the domain of this function would be A and B, and the supposed output would be 1, 2, and 3, but look what happens. This is well defined. What do we do with the number A? We take it to the number 1. But look at this. When I go to determine where should I send B, I could send B to 2, or I could send B to 3, and this is not a function. So that's why we need a function to be one-to-one, because if it's not one-to-one, then we cannot make the inverse. Although we can come up with this picture, it will not be a function, and that hopefully gives that explanation. Okay, so what I'd like you to do is I'd like you to go back to number 8, and for each question state whether or not it has an inverse. So I'm going to do 2 of these with you, and I'll leave you to do the rest. Okay? So this function is one-to-one, so f has an inverse. This function right here, sine of x, is not one-to-one, so j does not have an inverse. So I'll leave you to do the remaining 4. If a function is one-to-one, it has an inverse. If it is not one-to-one, then it does not have an inverse. Okay, so we've done a whole lot of discussion about when does a function have an inverse and what exactly do we mean by an inverse. But what we haven't yet discussed is how do we go find an inverse. So these are my steps to finding an inverse function. And before you do that, before you go to try to find an inverse function, I've hopefully driven home the point that you need to verify that this function is one-to-one. That's always your first step. Then this step is just notational, and then we're going to do this idea of swapping the x and y. That's related to this picture back here, this picture where when we go to construct the inverse, we take the domain, the range of the original function, and make it the domain. That's similar to this procedure of swapping the x and y, and then we solve the resulting equation for y, and then we call that f inverse. So let's go ahead and practice this here. So the first thing we need to verify is, yes, f is one-to-one. And we can see that because it's a linear function, its graph is a line. But before you go trying to find an inverse, because that can actually be, in these problems it won't be too hard, this can actually be a very challenging activity. Before you go trying to find an inverse, you need to verify that it's one-to-one. Okay, the second step says we're going to replace f of x with y. That's really just a notational step, and actually you could do this whole procedure without doing that if you wanted to. Okay. So we replace the f of x with y. Then we go ahead and we swap x and y. This is the interchanging of the domain and range. So I'm going to call x equal to 5/7 y minus 2. Then, now that we've done that, we need to solve the resulting equation for y. So I'm going to isolate the variable y here. So to do that, I'm going to add 2 to both sides. Lots of ways I could talk through this. I'll go ahead and multiply both sides of this equation by 7, which gives me 7x plus 14 is equal to 5y. And then I'll divide both sides of this equation by 5. So then lastly, my last step is to call this y f inverse. So here's our inverse function. 7/5 x plus 14/5. That's one way to park your answer. Other people might have parked their answer this way, 7x plus 14 over 5. Either of those ways are appropriate for parking your answer. So what I'd like you to do is I'd like you to mimic this procedure. This is actually almost virtually identical to the problem I just did, so give it a shot. Pause the video and try this problem. So hopefully you found the inverse of that. If you had any problems with that, please let me know. Let me know in class or come by and see me in office hours. So let's do another one. Okay. Now, here we have this function here. I don't think that it's necessarily clear that this function is one-to-one. If you were to go look at the graph of this function, the graph of this function actually looks something like this. It looks something like this. And it turns out that yes, h of x is one-to-one. Okay. I think it'd be a little bit hard to make that inference on your own, but I'm just telling you, we look at the graph here, we see that it is one-to-one. And you'll do the same thing when I have you try this problem. The first step will be yes, j of x is one-to-one. Okay. So now let's go ahead and find the inverse function here. So we're going to go ahead and say, well, y is equal to 2 times x minus 4 raised to the 5th power. We're going to swap x and y. So there I get x is equal to 2 times y minus 4 to the 5th power. And now I'm going to go about isolating the variable x. So, or excuse me, isolating the variable y. So to isolate y, the first thing I need to do is divide this 2 over. So this gives me x divided by 2 is equal to y minus 4 to the 5th. And now I'm going to take the 5th root of both sides of this equation. And so when I do so, I get the 5th root of x divided by 2 is equal to y minus 4. Finally, to solve for y, I'm going to add 4 over to the other side. And just reordering that, I get y is equal to the 5th root of x divided by 2 plus 4. My very final step is to call that f inverse now, so, or in this case, h inverse. So h inverse of x is equal to the 5th root of x divided by 2 plus 4. And there we found the inverse to this function h of x. Okay. So what I'd like you to do is pause the video and try number 16 on your own. And I'll see you in a moment.